Assalamu alaikum. Good day, everyone. Welcome to EAGE Local Chapter second webinar titled Velocity Modeling and Depth Conversion, a conceptual overview. Thank you all for joining. My name is Munira Al-Awadi and I'm going to be the moderator for today. So before we begin, I would just like to encourage everyone to become an EAGE member. It's a fantastic opportunity to stay connected and take advantage of all these resources as shown here. Additionally, if you're interested in staying updated with our upcoming events, make sure to follow us on our social media platforms. We regularly post and updates and announce there. So without further ado, let's get started. I would like to introduce our guest speaker, Mr. Kamran Laiq. He brings over 25 years of experience in the field of G&G. He worked globally with many companies. Currently, he is a principal geophysicist in SLB Kuwait as a part of SLB KOC with North Kuwait Jurassic Gas Team. He has several publications and he received several awards and recognition in SLB. So with this, I would like to give the floor to you, Mr. Kamran. You may share your screen.
Good afternoon and Assalamu alaikum everyone. My name is Kamran Laiq and I am working in Schlumberger, Kuwait as a principal geophysicist, and I'm also working as part of the Schlumberger team in the North Kuwait Jurassic project in Kuwait. So I would like to convey my sincere thanks, first of all, to EAGE and EAGE Local Chapter Kuwait for providing me this opportunity to present this webinar. This webinar is primarily designed for the new geophysicist or geoscientist, but at the same time it will also serve as a quick refresher for the experienced professionals as well. So I welcome you all for this technical session on velocity modeling and depth conversion, a conceptual overview on behalf of EAGE, a local chapter Kuwait. So this slide provides a quick overview of the seismic interpretation workflow, and out of this interpretation workflow, velocity modeling is an integral part of the geophysical interpretation workflow. So for any G&G work, it starts with data gathering, QC, preparing the project, and so this data gathering and QC will also serve as an input to our velocity models. It is extremely critical to use the properly QC'd data as an input to our velocity models for creating reliable velocity models and thus providing optimal results. So this session or this presentation will start with a quick background on why do we need the velocity models and what is their significance in the seismic imaging, geophysical interpretation, and reservoir description. The focus of this presentation or today's session is not about seismic processing, though it is extremely important to understand or recap different types of seismic processing velocities before we venture into velocity modeling. I will then go through the basics of velocity modeling and various approaches that may be used or applicable to address specific geological settings. Finally, in the end, I will show a few slides as part of depth conversion learning game to recap or review what we have learned during this session. So velocity models are the key components of seismic imaging and consequently to reservoir characterization. We can have different velocity modeling scenarios to test various geological uncertainties and unfold geological and G&G challenges. So integration of properly QC'd and tight seismic and well velocities is critical for the effective velocity models. When I say effective velocity models is because poorly constrained velocity models, the depth conversion errors may account for over 50% gross rock volume uncertainty, which eventually affect the volumetric estimation. So therefore, it is extremely critical to capture the velocity models and the G&G uncertainties properly when assessing volumetrics. So I've just mentioned briefly the significance of the velocity models. However, the two key or the basic objectives of any velocity modeling projects are to tie with the existing wells and to predict optimal depths at new well locations to be drilled. So the question arises, the geophysical interpretation is normally done in time, so why do we need to convert into depth in the first place? So as long as we are doing the seismic facies or sequence static sequence strat interpretation, we are okay in the time domain. However, it would still be more meaningful to have the results in depth. However, when we move to the structural interpretation, which is more riskier, as indicated in this cartoon, the figure or the cartoon on the left hand side, you see our zone of interest is just below the high velocity carbonates, which is the situation in reality. However, when we are working in time, because of the higher velocities just above our unit of interest, you can create a pseudo structure because of the velocity pull-ups. So it is really critical to properly depth convert the data, so we should not be misled by these pseudo structures. So in addition to the two basic objectives of velocity models, as I mentioned earlier, the other key applications of velocity models are to verify geological structures, confirm the structural traps, and once you have confirmed these structural traps, you can determine the spill points, estimate optimal gross thicknesses, volumetrics, and finally you can validate with the production data, and everything is in depth. So velocity model is a very simplistic cartoon, but it gives you the basic message that the velocity models bridges the gap between the time and depth domain. So the domain conversion basically workflow is a two-step process. A velocity model is defined, and then we do the domain conversion of different data objects. So the velocity, in order to define a velocity model, we start by defining the intervals based on zones, usually between time interpretation services. Then we define velocity functions. They can either be automatically calculated or user defined. Then we can have different outputs as part of the velocity modeling workflow, velocity Qs, V naught or K for QC purposes. And once we have the velocity model in place, we can do the domain conversion of a single object or multiple objects, or interpretation data as we like. So what actually depth conversion means? It has, as I have explained earlier, we need to build these velocity models in order to optimally depth convert the data in order to have a realistic subsurface picture. And velocity modeling, as we all know, it is an iterative process. We start with the very basic velocity model, and then we keep on adding additional data to capture a lot more uncertainties and to have a more robust velocity model in the end. It is important to have basic understanding of the seismic processing, but since it is not part of today's discussion, so we will not discuss it in detail, though we will still review and recap different type of seismic velocities as part of the velocity modeling background. So this slide gives you different type of velocities that we deal with. The average velocities, the interval velocities, instantaneous velocity, RMS or root mean squared velocities, stacking and DMO velocities, finally migration velocities. So I will explain each of these different type of velocities in these slides to come. But before we move on to defining or briefly describing the seismic processing velocities, let us quickly review the basic difference between the seismic and the borehole velocities in order to understand the constraints of both different type of properties. So as you can clearly see in this figure, the Checkshot velocities have better vertical resolution than the lateral resolution in comparison to seismic velocities. However, on the other hand, seismic velocities tend to capture a lot more lateral uncertainties. So in advanced velocity model, we make use of both these data sets to capture effectively the lateral and vertical velocities. So we have to understand both pros and cons, from both of these data sets, and make the best use of both the data sets in our velocity models. So now let us quickly review different type of seismic processing velocities. The average velocity is the simplest velocity, which is like defined as the depth z divided by the one-way seismic travel time t. And the key assumption while calculating the average velocity is that it has to be a vertical path and parallel layers and straight ray paths. These are the conditions which are quite idealized compared to the situation in reality. The interval velocity is the velocity of a specific rock unit, and it is calculated from sonic logs or from the change in stacking velocity between seismic events. So in contrast to interval velocity, instantaneous velocity is defined as a velocity over a very small interval or at a given moment of a wave front. They're also derived from sonic or acoustic logs. Typically taken, the readings are taken at every few centimeters in a borehole, so they're considered to be more accurate, or I would say more detailed. So it depends what kind of uncertainties you want to capture in your velocity model, and based on your objective, you can decide what kind of velocity property that you want to use in your velocity model. Now, RMS velocity, as the name indicated, is the root mean squared velocity, which is the value of the square root of the sum of the squares of the velocity values divided by the total number of values. So the important point to note here is that the RMS velocity is typically few percent higher than the average velocity across the same interval, and the key reason for that is the root mean squared velocity is the average speed of an object on a given axis, whereas the average velocity is the total distance traveled divided by the total time spent traveling that distance. So that is how RMS velocities, or that is why RMS velocities are slightly higher than the average velocities. Now, this stacking velocities is one of the very important types of seismic velocities. So stacking velocities are obtained during velocity analysis prior to stacking and are calculated as part of NMO correction on seismic trace gathers. NMO is actually the delay in arrival time because of increasing source receiver offset. This time delay introduces a hyperbolic effect in seismic gathers before NMO correction, as shown on the left hand side of this picture. You can see this hyperbolic effect, whereas the right hand side of the picture shows the same seismic gathers after the application of NMO correction. So NMO is basically the amount of correction required to flatten the event before they can be stacked. Another important point to be noted here that NMO is always performed in combination with DMO, which is the dip move out. In case of dip move out, the arrival times delay are caused by the geological dip, not by the offset, which is explained in the next slide. So this time delay, which is caused by the geological dip, also end up creating the hyperbolic effect, and similarly as in the case of NMO, we apply DMO to correct these geological dips. So finally, we talk about the migration velocities. So migration velocity basically optimizes the repositioning of the reflected energy to the correct location in the subsurface. Since velocities generally increase with depth, so errors in migration are usually larger for deep events than shallower events. So the steeper the dip, the more accurate the migration velocities need to be, since displacement is proportional to dip. So in the end, or as a summary, we can say the accuracy in event positioning after migration actually depends on the combined effects of the performance of the migration algorithm used and the velocity errors. So this slide just recaptures the velocity modeling overview, what we have learned so far at this point. So we start with QCing and validating the data, all the available seismic, well, or any other interpretation data. Then we define a velocity model by defining the intervals based on surfaces, constants, or and then we add on as much as details as depending on the data that we have. So we add well tops, time depth relations, velocity cubes, 3D grids, horizons, tight seismic velocities. So in order to build a more robust velocity model, once the velocity model in place, we can do the domain conversion either from time to depth and from depth to time. So this slide, at the end of every seismic interpretation or GNG interpretation workflow, we do the mapping, and once we have done the mapping in time, then we start with a simple velocity model, and then we go as the iterative process, as I've explained earlier. Then we start with the basic or the simple velocity model, and then we move on to the more advanced velocity model depending upon the uncertainties that we want to capture and depending on what kind of data we have available for a certain velocity model. So in the next slide, we will going to discuss the commonly used approaches for velocity modeling. So this slide basically recaptures graphically the same thing. We start with defining the intervals. We can do the velocity models with and without correction. And then we define these velocity functions. And finally, we can have the outputs as part of the velocity modeling QC. So now we will discuss different simple velocity modeling approaches. The simplest of the velocity models starts with seismic velocities, because if we do not have any well data, no surfaces, we can still have the seismic velocity. So as a first quick look velocity model, we can start with the simplest velocity model using the seismic velocities. It could be either V average or VRMS cubes. These velocities, we can start with the uncalibrated seismic velocities, and then we can calibrate these average velocity or seismic velocities to well velocities in order to have a better constrained velocity model. And then the other simple velocity modeling approaches is the single step velocity model or the direct calibration velocity model, in which we use gridded well velocities or either by using linear average velocity functions, often with correction grid to capture the lateral velocity variations. Similarly, the other approach, the simplest approach, is the layer cake velocity model. In this case, we create a velocity model using the constant interval velocities. Even in this case, we normally use with V0 grid to capture, the V0 correction grid to capture the lateral velocity variations. So this slide will give you a graphical picture of what we have just captured in the earlier slide. the various types of basic velocity modeling approaches. So this is a linear velocity. This velocity model is created using a linear velocity function, which is extrapolated laterally. So in this case, as you can clearly see, the velocity increases linearly with depth, but does not vary laterally. So in the next slide, you will see this is an example of a layer cake velocity model, but using only single check shot. And we create a velocity model using this single check shot by laterally extrapolating the velocity values from a single well. So in this case, this velocity model can be used as a first pass quick look velocity model. But the biggest uncertainty in this case, the uncertainty in the velocity progressively increases as we move away from the well with the check shot. So we can have a layer cake velocity model by using multiple check shots. Even in this case, we are laterally extrapolating the velocity values from multiple wells, and it is also used as a first pass depth conversion quick look method. So in this case, at least we are capturing a lot more velocities variations laterally in comparison to the single check shot version of the layer cake velocity model. However, even in this case, the biggest uncertainty is that the velocity uncertainty is less within the interval space, but as you go away from the interval space, the uncertainty increases progressively. Now, since we have already gone through the basic velocity modeling approaches, so now we can discuss which depth conversion method in general will be more applicable in a certain geological situation. So the single step depth conversion method is normally created using the time depth relationship or check shot data or V average, and they are usually considered appropriate for deep tertiary basins with clastic infill. They're not considered adequate if overburden contains thicker layers with lot of velocity variations. However, on the other side, layer cake depth conversion method is usually considered adequate in cratonic areas with condensed geology and substantial velocity contrast. To clarify what craton areas, you may already know, but craton is a stable interior portion of a continent, characteristically composed of ancient crystalline basement rocks. And this layer cake depth conversion method is not optimal next to or below mobilized salts or shales. So this is a simple figure, but it gives you a very intense message that I'm going to explain. So these are two classic velocity models, and these are a function of a depositional history of the geological environment in which we are operating. So geologically, we see a sequence of layers that are dipping away from the salt mass. Structurally, both the models look alike, but their velocity profiles are quite different. So in each case, the model on the extreme right hand side and the model in the middle, the colors grading from yellow to darker are intended to represent the increasing velocity. However, the diagram on the right side is what we call a compactional model. In this case, the rock velocity is a function of the depth of the sediment. So this means that the velocities do not vary laterally by a large amount in spite of the dipping or steeply dipping structure. This is typical of tertiary deposition basins, of which the Gulf of Mexico and Niger Delta could be the good examples. This is an important model because it is a typical model for current exploration. The model in the middle is called a layer cake velocity model. This is typical of older, well consolidated sediments. Each layer has a rock velocity that is characteristic of that particular geological unit. So one of the main causes of errors in depth prediction is mistype between seismic horizons and the corresponding geological well marker in time. So as shown on the left hand side of this figure, the direct methods, they basically have zero error at depth at the seismic and the well marker intersection. But these direct methods, they tend to hide these errors by forcing the well to tie at the intersection, whereas overall it gives you a poor predictability. However, on the other side, if you do not achieve a zero depth error at the well and the seismic intersection, but you have an overall better and good predictability. So those velocity models should always be preferred, which have overall good predictability rather than having a zero depth error at the well location. So there are always pros and cons of how much accuracy do you want at the well intersection, because as a general rule of thumb, everybody wants to have a zero error at the depth intersection or at the well intersection, whereas it is more important to have an overall good predictability. So once we have a velocity model in place, we can do the domain conversion of different data objects. It could be one object or multiple objects using general depth conversion. InPetrel and different applications have their own modules, but once we have a velocity model in place, the depth conversion can be done or performed either on one single data object or multiple objects. So this slide will basically give you a summary of what we have learned so far, or the domain conversion workflow. So we start with by defining the velocity model intervals. Then we define velocity functions. They can be either automatically calculated or user defined. And we start with the uncorrected velocity model, and then we apply correction based on well tops, surfaces, constants, and then once we have a simple velocity model, we can have the different kind of velocity modeling outputs in order to QC our data. And finally, once we have the velocity model in place, we can do the domain conversion, and after the simple velocity model, we can have a lot more robust and advanced velocity models depending upon the geological challenges and the amount of data that we have. So this figure or slide basically recaptures more or less the same thing what I've just explained. So we start with the uncorrected velocity model using surfaces, no correction, using a velocity function, and then we have a velocity model, and those outputs can be used to QC, and then and to QC our depth converted maps or the depth converted grid, and we can have the residual maps to define the uncertainty in our velocity modeling. And the second iteration could be to apply the well corrections. And then these corrections can be applied on constant surfaces, well tops, etc., etc., etc. So once we have our velocity model in place, we can do the domain conversion of multiple data sets. It could be grids, surfaces, horizon, fault, point data, seismic grids, seismic cubes. So the key deliverables of any depth conversion project are the maps and the grids in depth, the seismic data volume, or the seismic attribute volumes in depth, velocity model in SegY, and finally we can have the uncertainty analysis based on our residual maps, or we may have multiple velocity models to define the uncertainty in our in our calculations. So finally, we moving towards the end of our session, so we'll just go through some of the questions as part of the learning game. The idea of this learning game is to reiterate or recapture what we have learned so far in this session, just to to review what we have learned. So I'll start with a few basic questions. It won't take too much time, but as a learning exercise, let's start that. So the first question is, input to make grid surfaces can be of several types. Which of these types is not a suitable input? So we know that the grid surfaces can be created based on well tops, points, or horizons. So in this case, the correct answer will be the seismic cube. Now move on to the next question, which says surface attributes can be calculated based on a single horizon or between two fixed z values. So what could be the answer here? We know that the surface attributes cannot be created between two faults, between a horizon and a fault, or between points. So it is certainly the correct answer should logically be between two horizons. So when creating a velocity model in Petrel or any software, what is the next step after you QC the input data? We captured number of times in our session earlier that once we create a velocity model, or once we create a velocity model by incorporating all the data into the project, the first step is to define the velocity intervals, which is question number B is the right answer. So the answer number B is the right answer. So now moving on to the next question. So when defining a velocity model with corrections, which of these objects can be applied as corrections? And we have covered in our presentation. So we can have the simpler velocity model without any correction, but we can apply the corrections in the next iteration based on surfaces, constant, or well top. So the number D seems to be the right answer. The simple velocity model allows you to create a velocity model with only a dash as the input. And so we captured also during our discussion earlier. The simplest velocity model can be created based on the velocity cube. We may not have the well data or surfaces, anything, but at least as a processing velocity cube, we always get it as a byproduct of seismic processing. So the simplest velocity model we can have with the velocity cube, and we can start with a uncalibrated velocity cube, and we can have a second iteration with the calibrated velocity cube with respect to the well velocities. Finally, the last question is, the velocity model can be used to domain convert many objects. Select the ones that can be converted. So we know that once we have a velocity model in place, we can domain convert or depth convert any type of interpretation data, any grids, surfaces. So the correct answer is number D, which is this one. So finally, thank you everyone for listening to this presentation and to this technical session on velocity modeling and conceptual overview. I hope that you all have enjoyed listening to this presentation, and you must have gained or at least refreshed what you knew before. And I hope that it will be a useful session for you all, and inshallah I will meet with you all in the next session, which is on an advanced velocity modeling workflow that I will going to discuss in the next session. So thank you very much again for everyone. And so if any one of you has any questions or queries, you can always get back to me through EAGE Local Chapter Kuwait, and I'll be more than happy to answer any queries that you may have, regarding this presentation or even in general about velocity modeling. I'll be more than happy to assist or to help you or to answer your queries. You can always send your queries through EAGE Local Chapter Kuwait. Thank you very much, and good evening. Take care and see you in the next session. Thank you.